So let's start from scratch now and find a confidence interval for one proportion. Recall the central limit theorem from our section on distributions. We said that if we have these two conditions met, that n times p and n times 1 minus p both being at least 10, then it's reasonable to use a normal distribution to approximate the sampling distribution. The way that we use this with confidence intervals, we don't know the exact value of p, is we use n times p hat since it's our best estimate of p, and we use n times 1 minus p hat. So we consider this to be our condition for using a normal distribution. So that said, let's look at this example. A study found that 76% of 418 subjects who had received gastric bypass surgery maintained a 20% weight loss 6 years later. So we want to just generalize this to a population of everybody who receives gastric bypass surgery. Is it reasonable to assume the distribution for this sample proportion is approximately normal? That's really where this condition comes in. So we want to consider n times p hat and n times 1 minus p hat. N is 418, p hat is 0.76. So 1 minus p hat is going to be 0.24. I want to calculate both of these and see if both of them are at least 10. I can tell before I even start, just from that exploration we did with distributions, that these are going to be big enough because my n is pretty large at 400, and that 0.76 may not be dead center, but it's pretty close to center, and I would say that both of these are looking good enough that that we would expect to have a bell-shaped sampling distribution. But we'll go ahead and do the calculations. Sure enough, these are well over 10, so we would answer yes. Both of these are at least 10. All right, so we will go ahead and find a 95% confidence interval using the normal distribution methods. First, we need to find the standard error. That formula is the square root of p hat times 1 minus p hat over n, which in this case looks like 0.76 times 0.24 over 418, everything inside the square root. Putting that into a calculator gets me 0.0209. That's my standard error. After I get my standard error, I can find my margin of error. That's a z-star critical value times the standard error. Since I'm looking at a 95% confidence interval here, that tells me that my z-star critical value is 1.96. And my standard error is the number I just calculated. So we can now calculate this, and I get 0.0409. Now my p hat, sample statistic plus or minus margin of error, is 0.76 plus or minus, and like I said earlier, take it to 2 decimal places or 3, whichever seems more reasonable. In this case, I think 2 is fine since the next digit is 0 anyway. We'll go ahead and take that to 0.04 and get 0.76 minus 0.04 is 0.72. And when we add them, we get 0.8 or 0.80. So to interpret this, we want to think about generalizing to the population. We have a sample of people who received gastric bypass surgery, and we want to extend to all patients of gastric bypass surgery and say that the percent we would expect to maintain that weight loss is somewhere between 72% and 80%. Okay, so here's my statement with 95% confidence between 72% and 80% of all gastric bypass patients, making sure that we're making a statement about the population, not the sample, maintain a 20% weight loss 6 months after surgery. So if we had decided that it wasn't appropriate to use a normal distribution, now that's back to this step right here where we said n times p hat and n times 1 minus p hat are both at least 10. If one of those had come out to be less than 10 and we weren't sure it's appropriate to use a normal distribution, we couldn't use any of these formulas, but at this point we would go back to our bootstrap confidence intervals. The one that uses standard error still requires a bell-shaped sampling distribution, but the one that uses percentiles does not. So we would generate a bootstrap confidence interval using the percentiles method. That is not reliant on this bell-shaped curve. So this is our fallback method if our distribution theoretic condition does not hold. Just a real quick reminder of how that works. We would be doing a bootstrap confidence interval for a single proportion. We would want to edit our data to say that we had, I have to do a quick little calculation, 76% of 418, round to 318 out of a sample size of 418, and generate a few thousand samples. Click on to tail, and this gets us, sure enough, 72 to 80, same thing that we got, because our conditions were met. If our conditions hadn't been met, we wouldn't expect these to match quite so well.